is Lab 4, Macroscopic View of DC and RC Circuits. Before getting started, there are a few fundamental principles necessary to understand the rest of this lab. The first is Kirchhoff's second law, or the loop rule, which states that the sum of the potential differences around a closed circuit must be equal to 0. Next is the node rule, or Kirchhoff's node rule, which states that if a current is constant, all the current that flows through one junction must be equal to all the current that flows out of the junction. Last is the time constant of a circuit. This is the time at which the voltage difference has dropped to 1 over E of its original value. It's the product of the entire circuit's resistance in ohms and its capacitance in farads. This lab was quite long and had several parts, but there were a few core goals. We created several simulated circuits using an online circuit construction kit. We predicted and validated circuit behavior before and after manipulating elements. We used multimeters, such as ammeters and voltmeters, to measure current and potential difference at different points in a circuit. And then we examined the behavior of resistors and capacitors at the RC time constant. We looked at the resistor's effect on charging and discharging capacitors and the rate of discharge and charge of capacitors. The first part of the experiment looked at charge conservation and energy conservation in series circuits. We constructed a simple circuit in the simulator using 2 batteries, 2 ammeters, and 2 resistors. You can see screenshots of my circuit on the right. First, we predicted the current in the circuit. My calculations predicted that there would be 0.0204 amps running through the circuit, and when I inserted an ammeter into the circuit, I found my prediction to be validated. The next part of the experiment asked us to turn one of the ammeters backwards and see if the reading remained the same, which it did. Next, we replaced one of the ammeters with a voltmeter. The voltmeter read 3 volts, which is the potential difference coming from both of the batteries. When we replaced the ammeter with the voltmeter, the other ammeter read 0 amps. That's because the circuit was open, so no current was flowing. Next, we closed the circuit and used the voltmeter to measure the potential difference between different points on the circuit, as you can see on the middle diagram. Due to Kirchhoff's second law, we know that the sum of individual potential differences around the circuit should be 0, and my measurements in the simulator, as you can see in the table on the left, confirm that. Next, we used our simulated measurements to calculate the resistance in different circuit elements. We used the current of the entire circuit read by the ammeter, 0.02 amps. In order to calculate resistance, we used the calculation difference in potential over current. All of the calculations came out extremely close to the expected values, as you can see here. This is a graph of potential relative to the negative end of the battery versus position around the circuit using the measurements collected with the voltmeter in the simulation. As you can see, potential varies greatly as you travel around the circuit. Now, before we continue, there's a few things about the voltmeter that need to be addressed. When we attached it to the circuit, we altered the circuit, but the ammeter reading didn't change. That's because we attached the voltmeter in parallel and it has a high resistance, so very little current, if any, was able to flow through the voltmeter and change the ammeter reading. Then, in order to continue our experiment, we connected the voltmeter across the 100 ohm resistor, as you can see in the top picture. The ammeter read 0.02 amps like it did before. Now, if we replace the voltmeter with the ammeter in parallel with the 100 ohm resistor, the current through both ammeters rises to 0.06 amps. That's because the ammeter has less resistance than the voltmeter, and so the current value has to change. In the second part of the experiment, we looked at RC circuits, which means resistor-capacitor circuits. First, we had a 10 ohm bulb, a 9 volt battery, and a 200 millifarad capacitor. This is what happened when we connected them. As you can see, the light shines brightly at first, but then dims. It took the capacitor 17.88 seconds to completely charge, and the current slows to a stop as the capacitor charges. Now, when we have the same situation, but we remove the battery, this is what happens. The light shines brightly at first, but dims as the capacitor discharges. It took 18.91 seconds for the capacitor to discharge, and as you can see once again, the current slows to a stop as the capacitor discharges. Doing the same experiment with a bulb of double resistance, a 20 ohm bulb, shows that it took way longer for the capacitor to charge and discharge, 35.19 seconds to charge and 39 seconds to discharge. In the third experiment, we collected time-dependent voltage data across a discharging capacitor. We used a 30 ohm light bulb and a 200 millifarad capacitor. The capacitor had already been charged by a battery. We took time versus potential difference data of a discharging capacitor and then found the time constant. First, we calculated an expected RC time constant, which was expected to be 6 seconds. Then, using the data that we collected in the simulation that I've recorded to the right, we found how much time it took for the capacitor to completely discharge and at what rate is discharged. That's all graphed on the graph below. The light blue line is the change in voltage versus time, whereas the purple line is the linearized version. The linearized slope gives us the experimental RC data, or RC constant, which is 6.002 seconds, which is extremely close to our expected RC time constant. To conclude this lab, let's look at some fundamental questions that draw together everything we've learned through our simulation. What if we did this lab in real life and used a real ammeter instead of an ideal simulated ammeter? A real ammeter would have a resistance, so it would result in and record a smaller current. Now, what if we did this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? I ran a little simulation of what would happen in a simulation. As you can see, the capacitor charges instantaneously. This obviously can't happen in real life, so a capacitor cannot be charged without a resistor in the circuit. That's my lab. Thank you.